So in mathematics, we're going to consider a sequence simply to be a set of numbers arranged in a particular order. Usually you can write the numbers set apart by commas. For example, 1, comma, 2, comma, 3, comma, 4. That's a sequence of numbers. Now we're going to use sequences of numbers to also talk about a series of numbers. And a series is the sum of the terms in a sequence. For example, if I replace the comma with a plus sign, 1 plus 2 plus 3 plus 4, that's going to be a series. It's going to be a series which consists of the sum of 4 terms, t1 plus t2 plus t3 plus t4. And we call, again, the terms of the sequence just a subscript 1, 2, 3, 4, whatever term it is, and the t stands for term. So two basic types of sequences. They introduce you to a whole bunch of sequences here in this first section, but two that they're going to focus in on are what are called arithmetic sequences. And perhaps you've seen these in Algebra 2 before, perhaps not. Arithmetic sequences and geometric sequences. Now basically, the difference is to get from one term to the next in an arithmetic sequence, I have to either add or subtract a common difference. For example, 3, 8, 13, 18. If I tell you that's an arithmetic sequence, the common difference between each two terms, in other words, the fourth term minus the third term is 5, the third term minus the second term is 5, the second term minus the first term is 5. I also could say that 20, 18, 16, 14 is an arithmetic sequence, and the common difference in this case would be -2. 18 minus 20 is -2, 16 minus 18 is -2, 14 minus 16 is -2. And generally we use D to stand for difference. So for the first one, our D is going to be 5. For the second one, our D is going to be -2. So a geometric sequence, on the other hand, to get from one term to the next, you have to multiply by a number. So for example, if I give you 1, 4, 16, 64, 256, and tell you that's a geometric sequence, clearly each time I'm multiplying by 4, and we say that the ratio between the nth term and the nth minus first term is 4. Note that 256 over 64 is 4, 64 over 16 is 4, 16 over 4 is 4, 4 over 1 is 4. I could also have a number be a negative number and maybe not even be a number less than -1. For example, I could give you 1, -1/3, 1/9, -1/27, 1/81. And in that case, my R is going to be -1/3. How do I get from one term to the next term? I multiply by -1/3. Note, with my R in a geometric sequence being negative, I'm going to alternate positive, negative, positive, negative, positive, etc., etc. And again, my ratio, 181 over 1/27 is -1/3. -1/27 over 1/9 is -1/3. 1/9 over -1/3 is -1/3. -1/3 over 1 is -1/3. And we refer to that as R. So, we're going to be interested in, first of all, to start off with what are called explicit formulas for arithmetic and geometric sequences, or a sequence in general. For example, suppose I give you, this will not be arithmetic or geometric, but suppose I give you the sequence which is as follows. 1 over 2, 2 over 4, 3 over 3 over 8, 4 over 16, 5 over 32. Can you guess what the next term is? Pause it. Okay. Next term is clearly going to be 6 over 64 if we follow the pattern. So what's a rule for our nth term. Our nth term is going to be n all over 2. Let's see, the first term we had a 2, so 2 times 1. The second term, 2 times 2 is 4, or 2 times 2 is 4. The third term we had, well, let's see, it wasn't 2, it was 2 cubed. Oh, let's see, so 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So it's actually not multiplying down here, it's going to be 2 to the n. And then I look at this sequence and say, is this sequence geometric or arithmetic? And the answer is it's neither. I don't multiply or add or subtract the same thing to get from one term to the next. So I can come up with what's called an explicit formula for the nth term of the sequence, but the formula is neither arithmetic nor geometric. So to come up with a formula, an explicit formula for the nth term in an arithmetic sequence, basically the idea is you're starting with the first term and you're adding that d to get to the next term. So to get from the first term to the second term, I'd add 5, which would be 1d. To get from the first term to the third term, I'd have to add 1d and another d. I'd have to add 2d. To get to the fourth term, I'd have to have 1d, 2d, 3d. So in other words, to get to the nth term, I start with my first term and I add n minus 1 d's. And that is my formula, explicit formula for the nth term of an arithmetic sequence. How about for a geometric sequence? Same reasoning. Start with your first term. To get to the next term, I multiply by r, which in this case is a half. To get to the third term, I'd have to multiply a half and then multiply a half again. So I'd multiply by a half squared to get to the third term. To get to the fourth term, I'd multiply by a half, a half, a half. I'd multiply by a half 3 times to get to the fourth term. So therefore, in general, the nth term is going to be given by my first term times r to the n minus 1. And that's my formula for the nth term, explicit formula for the nth term of a geometric sequence. So, suppose we've got, we're given the second term of a sequence is 2, and the fifth term is 16, and I'm asked to find an explicit rule for the nth term, assuming the sequence is either arithmetic or geometric. So let's assume arithmetic. To go from the second term to the fifth term, I know I'm going to add 3 differences because I got to get the second to the third, then I got to get the third to the fourth, then I get the fourth to the fifth. So I know 3 differences. That's 16 minus 2 equals 14. 3 differences have to account for 14 units. So therefore, my difference is going to be 14 thirds, is going to be D. So then I'm going to have to find, if I want to find an explicit rule for the nth term, I'm going to need to find what T1 is. Well, I know that T2 is 2, so T1 is going to be 2 minus 14 thirds. So that would be, let's see, 6 thirds minus 14 thirds is negative 8 thirds. So I've got then my nth term, it's going to be the first term, negative 8 thirds, plus, sorry about the phone, 8 thirds plus n minus 1 times d, and we said our d is 14 thirds. So there's an explicit rule for the nth term. I then could go ahead and find, you know, T14 or T3 or T22 by simply plugging in n equals 22. Might not be fun arithmetic, but I could do it. So suppose we want to assume that the series, instead of being arithmetic, is geometric. It means that to get from T2 to T5, I'd have to multiply by my r 3 times. So that would mean then that 2 times r cubed is going to have to give me a 16. So r cubed is going to have to be 8, and then r is 2. So therefore my rule for the nth term is going to be Tn equals first term. Well, let's see. The first term would mean I'd have to take my second term up here, divide it by r to get to the first term. R is 2, so 1 times r in this case was 2 to the n minus 1. And so there's my explicit formula if the sequence were geometric or if the sequence were arithmetic. Now we can talk about graphing a sequence, arithmetic or geometric sequence, and we got to think about the fact that we're going to be graphing a set of discrete points. For example, if I tell you that Tn equals 1/10 to the n, and I ask you to graph that set of points starting with T1. So in other words, I'm going to have on my x-axis, I'm going to have 1 for T1, 2 for T2, 3 for T3, 4 for T4, etc. And I go, okay, if I plug a 1 in, I get 1/10. So at 1, I get 1/10. At 2, I get 1/100th. At 3, I get 1/1000th. And note my graph of a sequence is going to consist of a discrete set of points, where on the x-axis, I've simply put my term number, 1, 2, 3, 4, for T1, T2, T3, T4, and my y-axis represents the output, the Tn outputs, and you graph a discrete set of points. And finally, something for you to think about. Suppose I give you an arithmetic sequence, something like Tn equals 4 minus n minus 1 times 2. If I go ahead and expand that out, I would get 4 minus, over here, let's see, I have a 2n minus 2, and if I expand my negative through, I get a 4 minus 2n plus 2, so I'd get a negative 2n plus 6. And I'd like you to look at that for a minute. Tn equals negative 2n plus 6. What kind of function, if I were to think about this looking something like y equals some function of n, it's kind of looking like an mn plus b, or an mx plus b. So it looks like the discrete set of points that is the graph of a arithmetic sequence is indeed part of, if I were to consider an associated line, a continuous line letting n be any real number. In other words, graphs of arithmetic sequences are subsets. They're discrete points on the graph of a line.